This is the second PowerPoint in this series. Once again, there'll be worked examples and commentary as you work your way through this, so proceed on to learn about the truncus. Today we're looking at the graph of the truncus. The truncus basic form is this one here, which is y equals 1 on x squared. Up here in the heading you can see this is the form where we have our normal dilation from the x-axis at the top, our translation along the x-axis, and our translation along the y-axis. You'll notice here the x take b is inside the squared. Truncus is basically 1 on x squared, as pointed out down here. So the x take b part has to be inside the bracket. Alright, so let's see how we attain these values. So if I put -3 into the rule, I put x equals -3 in the rule, 1 on x squared, I get 1 on -3 squared. And when you square a negative number, you get a positive answer. So this becomes 1 on 9. So that's that answer there. So if I put -2 into the rule here, I get -2 on the bottom, and square that makes +4, so the answer here is +1/4. If I put -3 on 2, I'll do this one here, so that's 1 on -3 on 2 all squared. It's very easy doing this with a mouse. Anyhow, this becomes 1 over -3 squared is 9 over, better make that look like a 9, yep, over 2 squared is 4. So it turns into a positive number. When you square a negative number, you get a positive. So 1 on 9/4 is this, and the rule of fraction here, you flip the bottom fraction, so the answer is going to become 4 on 9. So a bit of a review of our fraction work there. That's where that answer 4 on 9 is coming from. If I put -1 into the rule, which is the next one, which is here. If I put -1 into the rule, -1 squared is +1, so 1 on 1 is 1. Put -½ I'll do that one here, 1 on -1/2 squared. So it's the same as top doesn't change, it's 1 over. Negative times a negative is positive, so the bottom becomes 1/4. And how many quarters are there in 1? There's 4. So that's where we're getting these values from. Same argument to get 16 there. Once again, we cannot divide by 0, so if I have 1 on 0 squared, we get 1 on 0. That has no meaning in mathematics, so we say it's undefined. And you'll see here that these values here are symmetrical with these ones here. And unlike the hyperbola where we had some were positive, some negative, with the truncus, because of the squaring, we end up with the same sign. They're all positive here. Alright, so that's where this table of values comes from. We'll proceed to the next slide. So now we can plot the values that we've just worked out. So I'm going to do that and see what our graph looks like. So when x equals -3, y equals 1/9. I've only got only out to -2 on the graph here. So let's start at -2 to 1/4, which so that would be that coordinate there, somewhere like that. The next one, if I put in x equals -1/2 or 3 on 2, y equals 4/9, which is just a little bit less than a half, so that's where we'd put our point. Next one, when x equals -1, y equals +1, so we'd get the coordinate there. When y equals -1/2, when x equals -1/2, y equals 4, so it's way up here. So you can see when quarter it's going to be +16, we can't plot that point. It doesn't equal 0, so just like our hyperbola, we say that the graph's never going to equal when x equals 0, so we put a vertical asymptote on the graph. And we'd label that. That's got the equation when x equals 0. On the next slide, I've got the graph, what it should look like. So this is just a to show you how to get the values. All right, so if we go over to the positive values of x now, when x is a quarter, y is 16. I can't plot that point on this grid. When x is a half, y is 4. I can plot that point. That's this point up here. When x is equal to 1, y is equal to 1, so I can plot that point there. When x is 1.5 or 3 on 2, y is 4/9, just a little bit less than a half. So about there, be appropriate. When x equals positive 2, y equals a quarter, so it's about there. Okay, it's a curve, so I'm going to join the points on the left-hand side of the... Oh, I've missed that there, should have been going through that point. But you'll get the idea. And it's a bit harder with a mouse than it is with a pen or a pencil. And on the other branch we come down through these points like this. It's a bit better. Put arrows on each end in case the graph keeps going like that. And what happens down here, it looks like the graph is approaching the x-axis, but there's no value of x that will make y equals 0. So once again we get a horizontal asymptote. So the truncus, like the hyperbola, has two asymptotes. The standard one without any translations is when x equals 0 is the vertical one, and the horizontal asymptote is when y equals 0. Alright, that's the general shape of what a truncus looks like. It's called a truncus because it looks a bit like a tree trunk. And because my graph's a little bit rough and ready there, it looks more like a tree than probably what the curve should look like. When we look at the next slide, you'll see how smooth the curve should look, but this is a bit hard to draw with just a mouse. Okay, we talk about the domain is what x values. Right, so the domain is what x values we can use in this graph. On this graph we can use all x values, so we say all the real numbers, but there's one value we can't say, so we say excluding, backslash, curly bracket, and the value in this graph we can't use for x is 0. Okay, the range, in this case though, I've only got positive values of y, so there's a couple of different ways this can be written. One way would be to say y is greater than 0. That's not really the preferred method. We could say it's r plus, that is only positive real numbers, or, that is an or, we can say it's round bracket 0, comma, all the way up to infinity, because the graph keeps going up as high as possible. Okay, so we've got little things to fill in here. So here the vertical asymptote is the y-axis, and the equation of asymptote is x equals 0. Remembering that all vertical lines have the equation x equals a number. So the horizontal asymptote here we can see is the x-axis. And the equation of this asymptote is x. It's not going to be a very good x equals 0. Once again, if you look at the next slide, you'll see that looks a bit easier to read. So let's go across to that. This is what your graph should be looking like. Nice, smooth, continuous curve. You can see here it's all nice and smooth and continuous. All right, going through those key points we watched before. So the key points actually are here, which is the coordinate -1, 1, and the matching coordinate over here on the other side is, for want of a better dot there, 1, 1. Right, smooth continuous curve, two asymptotes or dotted lines. Vertical one, the equation written there next to it is x equals 0, and the horizontal asymptote is y equals 0. What you need to fill in your notes is that the domain is all real numbers excluding 0, the range is r plus. The vertical asymptote is the y-axis. The equation of the asymptote is x equals 0. That's this here, the red dotted line. The horizontal asymptote is the x-axis. The equation of the asymptote is y equals 0, which is our blue dotted line there. Transformation for the truncus are exactly the same for all other graphs, so the A, B and C do the same things, and we've got to remember to label our asymptotes with their equations. Here we have two examples to sketch both these graphs and labelling intercepts with their axes with their coordinates and state the domain range. So first thing I'm going to do is underline the things that I need to do. I need to sketch, I need to label any intercepts, that's x and y, with their coordinates, and we also need to state the domain and range. There's quite a few things we need to do here. So at the end of the question, I'll just look back there. This slide here is going to have the working out, and the next slide will have the finished product. All right, so let's look at this first one here. When I look at this, I see that the A is equal to 1, so therefore there's no dilation. The graph is it's going to be the same shape as the standard truncus, 1 on x squared, but I can see here that there's a plus 1 next to the x inside the squared, inside the bracket. This means there's going to be a translation of 1 unit to the left. This plus 1 at the end is going to cause a translation upwards of 1 unit. Okay, so if I was drawing this graph here, the first thing I do is draw my axes, x and y, label them. We had a ruler, we should be using a ruler. My little program here doesn't allow me to do that, so that's the best we do. So if this graph has been shifted up 1 unit, then the horizontal asymptote has been moved up 1 unit. So this would have the equation y equals 1. The vertical asymptote, which originally is on the y-axis, has moved 1 to the left, so next thing is I'd put in the vertical asymptote here, and this is now at the value x equals -1. Alright, it's a truncus. It hasn't been dilated and hasn't been reflected, so it's a positive truncus graph, so it's going to be looking like this. A bit smoother than that, obviously, but I'm restricted by the mouse, and it's going to come down like this, which means we've now got a y-intercept, which I need to calculate. Y-intercepts are calculated by putting x equals 0 into the rule. If I put x equals 0 into this rule, the rule becomes y equals 1 on 1 plus, 0 plus 1 all squared plus 1. So it makes y equals 1 over 0 plus 1 squared is 1 squared, which is 1 plus 1. 1 on 1 plus 1 equals 2. So this y-intercept here is the coordinate 0, 2. There's no x-intercept because the truncus has the 2 branches here and won't go lower than this. So we're asked to sketch the graph, labelling intercepts, we've done that. With their coordinates, we've done that, 0, 2. State the domain and range. Well, the domain is what x values we're using in this graph. I can put into this rule here all x values, so we say r represents all x values, excluding backslash curly bracket. What x value are you not allowed to use? -1, because if I try and put -1 into this rule up here, we end up with, on the bracket on the bottom, we end up -1 plus 1 makes 0, and I'd be trying to divide by 0, which we can't do in mathematics. So that's why the domain is all real numbers excluding -1. The range is what y values we're using. Okay, this graph comes down and approaches the y value of +1, but never reaches it on both sides, but it goes upwards. If you can see here, it goes upwards to positive infinity. So we say the range is round bracket to 1 to indicate that it doesn't equal 1 up to positive infinity. And we don't know the value of that, so we use a round bracket also. So that's the first graph. When you look at the next slide, you'll see a much better version of that graph. Part B. Now there's two things. There's a few things we're going to be aware of here. First thing is this. There's a negative out the front. So that causes a reflection in the x-axis. This -2 in the brackets will cause a translation to the right 2, and this +3 at the end will cause a translation up by 3. Okay, so we can start sketching our graphs here by drawing a set of axes. Okay, there's my x-axis and my y-axis. The graph has moved 2 units to the right, so that means the vertical asymptote is going to be moved 2 units to the right. So it's going to have the equation x equals 2. The horizontal asymptote has been moved up 3 units, so that's going to be the horizontal asymptote. That's at y equals 3. Alright, in this time here, our truncus, because it's been reflected, it's going to be look more like this. Upside down truncus. That's what the reflection in the x-axis does. But our graph will probably be cutting through the y-axis somewhere between the asymptote and the x-axis, and then cutting the x-axis between the vertical asymptote and the y-axis. But to confirm that, I need to find the intercepts. So first of all, to find the y-intercept, we put in x equals 0 into the rule, so it's going to be a y equals 1 over, it's actually -1, there's a negative at the front, -1 over 0 take 2 is -2, putting 0 for x in the rule, squared plus 3. So that makes y equals be -1 on a quarter plus 3. So that equals 2 3/4, or 11 on 4. It's pretty easy for me to write it, 11 on 4. So 3 minus a quarter is 11/4. So the y-intercept is going to be here. The coordinate there, I'm just going to write it like this. When x is 0, y is going to be equal to 11 on 4, or that's 2 3/4. Right, so obviously my truncus is coming like this and cutting down through here. Try and make it as smooth as possible. Therefore, the other branch of the truncus should be looking like this, because they are symmetrical about that vertical asymptote. Right, but this shows me that I've now got 2 x-intercepts. Okay, so now I'm going to show you how we find the x-intercepts. Just change colours so it doesn't get too confusing. So we put y equals 0 into the rule to find x-intercepts. So this leaves me with -1 on x take 2 all squared plus 3 equals 0. Alright, next thing is to solve this, we need to make it one term on each side, so take the 3 over the side, so I get -1 on x take 2 all squared equals -3. Where am I going to draw this? Alright, we might have to go up to this blank space up to here. Sorry about that. Alright, so the best way to solve this is this now becomes -1 over -3 is equal to x take 2 all squared. I'll explain what's happened there. Down here, this is all on the bottom, so it becomes a multiplier up there, and that -3 will be multiplied by that bracket, so I can then divide both sides by -3. So effectively the quick way is those two just swap positions. So but it's doing two steps in one. Right, a negative divided by negative makes that positive, which is good. So 1/3. We now need to get rid of the squared, so I'll go back to yellow here. So we're going to have the square root of, well, I think we just had gold before. 1/3 is now equal to x take 2, but that's not quite correct. Whenever you take a square root, there's a possible to have a positive answer or a negative answer. So there's actually two answers here. As we can see from the graph, we've got two x-intercepts. And then the last thing is we take the 2 over the other side. So the limit of x on this side is equal to, that'll be +2, so we might as well write it as 2 plus or minus the square root of 1/3. It's easy to write the 1/3 and put the square root around it. Okay, that's two answers. 2, which is actually the vertical asymptote, and I'm going positive square root of 1/3 that way, and taking away square root of 1/3 that way. On a calculator we can get the approximate values of those answers. But if we had to write these with their coordinates, then this coordinate here would be 2 plus the square root of 1/3, comma 0. And this one here would be 2 minus the square root of 1/3, comma 0. So I'll write that here, 2 minus the square root of 1/3, I'll put the third first, then do the square root, comma 0. Just a little note here, and I'll just do it over here. The square root of 1/3, if you remember your third work, is the same as the square root of 1 on the square root of 3. So this is also the same as 1 on root 3, and we can also rationalise the denominator, and this would become root 3 on 3. Your calculator can do that for you. If you can't remember how to rationalise the denominator, you need to multiply this here by root 3 over root 3. And you end up with that answer. Okay, if we go on to the next slide, we can see a much better version of all this working out. And there we go. Except you see I haven't labelled the axes with the intercepts, which I'd done on the previous slide. But it's much neater, you can see much better there. You can add those intercepts to your graphs and how to work them out like I did on the previously. And also we need to talk about the domain and range for the second graph. The domain is all x values going on here except this value here, x equals +2. So that's why we say R excluding +2. The y values and used in this graph are going from there downwards. So the highest value there is 3, but it's never equal to 3. That's what that asymptote indicates. So we always, when we do a range or a domain using the interval notation like this, always do the most negative value first. So this is going down to -∞, so I write -∞ first, comma, and what goes upwards goes up to -3, +3, and it's going down to -∞. So we always say from the most negative to the most positive in that direction. So that's the range there. Thank you. Now you should be able to proceed with the questions for this topic. This is a truncus of the general form y equals a, all divided by x, take b all squared plus c. So we've got our sliders where we can change the values a, b and c. So let's investigate first what happens when I change the value of a. So the standard one here at the moment is the graph of y equals 1 on x squared, and go through the key points: negative 1, 1, positive 1, positive 1, and it has the horizontal asymptote of y equals 0 and has the vertical asymptote of x equals 0, but I can't label this for some reason. We'll just have to cope with that. So as I change the value of a, we find that the truncus is dilated from the x-axis by a factor of a. In this case it's a factor of 2. That point now is twice as high, so is that one, as the original one when a was 1. If I make a 3, you can see now the point has now been dilated by a factor of 3. It doesn't change the basic shape of the truncus, still has that trunk looking, still has the vertical asymptote and also has the horizontal asymptote at x equals 0 and y equals 0. So a causes the graph to be dilated. If a is negative, we see that the graph is reflected in the x-axis. Asymptotes don't move. If I make a equals negative 2, we can see it's been reflected in the x-axis and dilated by a factor of 2 from the x-axis, twice as far away after I've reflected it. So you can see that there. So if we make a negative 4, for instance, we can see that now the graph is being reflected because of the negative and also dilated by a factor of 4. So if a is negative, there's two things happening there: a dilation and a reflection. Alright, let's go back to where a equals 1, our standard truncus graph. Here it is. That's 1 on x squared at the moment. Now I'm going to investigate what happens by changing the value of b. If I make b positive 1, the truncus has been moved 1 unit to the right. You can see here that point that originally was negative 1, positive 1, now is 0, 1. This point here is what happens when x equals negative 1, because that was one of their standard points to start with. If I make b 2, the graph has moved 2 to the right. This vertical asymptote would now become the equation x equals 2, which say the domain is r excluding 2. That original point over here, which was a negative 1, positive 1, has been shifted 2 to the right, now becomes positive 1, positive 1. And that's the y-intercept here, which you could work out by putting x equals 0 into the rule. So we'd end up with 1 over negative 2 squared, so that becomes 4, so 1/4, 0.25. And the value when x equals negative 1 is still sitting there, because that's a part of the way I set up the program originally. So if I move b even further to the right, you can see now the asymptote is now at x equals 3. That point 1, when x equals 1, the coordinate now is 1, 1/4. So if you put 3 into here, you'll get an x equals 1, you get a 2 on the negative 2 on the bottom, but squared makes positive 4, 1 on 4. That's why when x equals 1, y equals 1/4. Okay, so we can see by making b positive, it translates the graph to the right. If I make b negative, so this is back to the standard truncus graph, if I make b negative, it actually shifts the graph to the left, translates the graph to the left. So here's when b is the value of negative 1, so in the bracket it's going to look like x. Take away negative 1, take away a negative makes it plus. So this rule at the moment would be 1 on x plus 1 all squared. And we get the vertical asymptote at x equals negative 1, and the graph moves it to the left. So if I just keep making b more negative, you can see the graph gets pushed further to the left. I'm going to put b back to 0 for the time being, and there we've got that standard truncus graph. Now I'm going to see what happens when we change the value of c. So if I make c a positive number like 1, can see the whole graph has been moved up 1 unit. Those key points of -1, 1 now becomes -1, +2, and the key point of 1, 1 now becomes the point 1, 2. We've added 1 to the y values. All the y values being pushed up by 1 unit. So the horizontal asymptote is y equals 1, x equals 0 still here. The changing c doesn't affect the vertical asymptote, it affects the horizontal asymptote. So it makes c bigger. You can see it just moves the graph up. If I make c less than 0, so for example -1, the whole graph has been translated down 1 unit. So those key points now, -1, -1, +1, which was here, it's been dragged down 1 unit, and actually becomes the x-intercept of this graph. So this graph here would be, the equation would be y equals 1 on x squared, take 1. If I make c, -2, we just keep bringing the graph further down, and the horizontal asymptote moves down with it. Alright, so I'm going to go back to the last equation, the last example we did, where we had b had a value of +2, a had a value of -1, and c had a value of +3. So that was the second example in our notes, and roughly that was the graph that we drew there. We can see from here it's got a bit all over the place, but we can see here the graph goes to the coordinate 1, -1, that's that orange point there. The x-intercepts are 2.08 and 0.92. You can see those two values are symmetrical about the vertical asymptote there at x equals 2. They're both 1.08 approximately away. I think we said in our notes those values were +2 plus or minus 1 on 3, the square root of 1 on 3, which must approximate roughly to about 1.08. Oh, sorry, to 0.08. I haven't got B, sorry. B was 1.5, I've got B2 now. So they're approximately symmetrical about the line x equals 2, about 0.58 either side, those intercepts. The y-intercept we worked out as 2 3/4 before, and there's a couple other key points that this graph goes through. It goes through the point 1, 2, because that's the coordinate 1, 1 has been moved, the coordinate -1, 1 has been moved 2 to the right, becomes +1, then up 3, but it's been a reflection as well, so it's actually in order. We would have gone like this. So if I make these zeros, this is probably a better way to explain this to you. First of all, we reflect the graph, so the key points are these two coordinates here. This one's actually coming down to here. -1, -1 now, because originally it was -1, +1, it's been reflected in the x-axis, and the original point up here, 1, 1's been reflected in the x-axis, becomes 1, -1. Then I would move the graph 2 to the right, so 2 to the right, so that point that was over here now becomes 1, -1. We've actually lost the coordinate over here, would have now become 3, -1, be sitting here. And then I need to raise these by 3 units, and that coordinate there, 1, 2, is the original point here, which was -1, 1, reflected over here, moved to the right, up 3. The one at 1, 1 moved, reflected to here, moved 2 to the right, and then went up 3. So we'd have the coordinate 3, 2, but it doesn't show it on this little thing. Okay, so I think that's enough for that there.